Steve, do you know what math is?
Not really, Sophie.
Do you want to learn?
Sure.
Great!
Do you want to learn with a hands-on experiment that we did involving a handmade catapult?
Absolutely.
Sweet, let's begin!
So, a little bit of brief history on catapults. The catapult is a device invented by the ancient Greeks that has been proven to be one of the most effective mechanisms during warfare. Because of this, they were used during World War I for flinging hand grenades. Okay, so first we wanted to explore projectiles and how they move, so we decided in the beginning of class to start building a catapult. So first thing we did was build a small scale model out of popsicle sticks, and we used super glue, and our projectile was a marshmallow. First we videoed the marshmallow being flung.
Okay, one more.
And then we used Logger Pro to analyze this video. We set the origin on Logger Pro to the ground line so that we could get a more consistent graph that visually showed us exactly where the marshmallow hit the ground. Then we found the roots by using the quadratic equation. The roots are 1.77 and 2.51. This process showed us when the marshmallow hit the ground. We then solved for the distance. We plugged in the y root, which was 2.51, into the quadratic equation and solved for x. We then knew that the marshmallow hit the ground at 0.929 meters. Just on a side note, in this graph, you can see that the slope is negative. This is only because the slingshot is flinging to the left. So, how many points do you think we need? We actually need 3 points to get a quadratic formula or equation, because in quadratic formulas or equations, there's an A, a B, and a C.
Based on our small-scale model, we decided to build a larger model and fire it using a tennis ball. It took us a few tries to figure out the most effective way to fire it. Then we analyzed the video using Logger Pro. We set the origin on Logger Pro to the ground so that we got an accurate measurement of where the ball hit the ground. Then we found the roots by using the quadratic equation of negative b plus minus the square root of b squared minus 4ac all over 2a. The ball left the catapult at 4.9 seconds. The roots are 6.97 and 4.97. This process showed us when the ball hit the ground. We then solved the distance. We plugged in the y root, which was 6.97, into the linear equation. We then knew that the ball hit the ground at 14.609 meters.
At first we started with rubber bands and a shorter arm than the one we have now. We didn't get the distance we wanted, so we extended the arm, used a block and tackle pulley system, and used surgical tubing instead of physical therapy bands. A block and tackle's mechanical advantage is the number of parts of the rope that act on the load. The mechanical advantage of a tackle dictates how much easier it is to haul or lift the load. The mechanical advantage of a block and tackle is equal to the number of parts in the line that either attach to or run through the moving blocks. A line with a mechanical advantage of 3 has a velocity ratio of 3 to 1. In other words, to raise a load at 1 meter per second, the hauling part of the rope must be pulled at 3 meters per second. Therefore, the mechanical advantage of a double tackle, which we had, is 3 times easier to pull than it would be without a block and tackle. To put that in perspective, without the block and tackle, we would have been pulling 137.5 pounds instead of 45 pounds.
For our small catapult, the marshmallow traveled 0.929 meters, and for the large catapult, the tennis ball traveled 14.609 meters. This, in total, it was an increase of 13.68 meters. For the small catapult, the base was 0.23 meters, and the large scale base was 2.3 meters. And for the small catapult, the arm length was 0.345 meters, and for the large catapult, it was 4.35. The large model's base was 10 times bigger than the small model's base. The large model's arm was 12 times bigger than the small model's arm.
For our small catapult, in 0.74 seconds, it traveled 0.92 meters at a speed of 1.24 meters per second. For our large catapult, in 2 seconds, it traveled 14.609 meters at a speed of 7 meters per second. The large model fired its projectile 5.6 times faster than the small model did.
For our small catapults, the force applied was 0.88 pounds, and for the large catapult, the force applied was 137.5 pounds. 156.25 times more force applied to the large than the small catapult. I learned how to use the quadratic formula and that you only need 3 points in a parabola to find where the object in motion will land on the ground. You need the A, the B, and the C.
I learned that for a catapult to fling a projectile the farthest that it can, the tension needs to be very high, the friction needs to be low, the arm needs to be long, and the object thrown needs to be light.
I learned that you can apply quadratic formulas and parabolas into real-world experiments like catapults.
And we learned that
Math is fun!